I'm going to deal with some field techniques or how we go about collecting water samples, soil samples from the environment, what methods are used, a little bit of protocols, and what kind of things are typically looked for contaminant-wise in my experience in the work that I've done on First Nation lands. So again, a little introductory about potential impacts, sort of the common ones that we deal with to First Nation lands, a little discussion of their sources, and very briefly about their effects. And then discussion of how we go about collecting those samples, what processes, what tools, what instruments we use, and we've got a little bit of our meters and probes and monitoring equipment here that we can show how they work afterwards. So the first section will be a little bit about common environmental impacts to water and soil in First Nation lands, sources and effects. So the first section I've called is chemical products, sort of those things that are man-made, they're not naturally found in the environment, consumer products, industrial products, chemicals that are used in everyday life, commonly used, and through spills and releases and accidents, they're released to the environment and they can become a problem in the environment. The most common, and we'll talk about is sort of the group called petroleum hydrocarbons. That can include gas, diesel, avgas, motor oils, hydraulic oils, those kind of things. PCBs, everybody's heard of PCBs, polychlorinated biphenyls. They're not used as much anymore, but historically the problem exists. So they're still out in the environment. They're very persistent, so they stick around, and they have some special problems with them that I'll discuss when we get to that section. Solvents, which can be cleaners, it can be in oil-based paints, those really light products. Wood preservatives can be an issue, and then glycols and antifreeze. And there are more. These are just some common chemicals that you might run into with environmental concerns. So petroleum hydrocarbons, this is probably the focus of what we deal with the most. They're commonly used everyday life. There's large quantities of stored and used to fill your car up, to heat your houses, to lubricate your equipment. And again, those are some examples of the petroleum hydrocarbons. And issues are usually related to storage and handling, and then waste management. Oftentimes these products become waste, and the waste has to be handled as well. Pardon me? I'll just do it? Okay, sure, that's great. So some problems with petroleum hydrocarbons from an environmental or health perspective. From humans, short-term exposure to vapors can cause nausea, headaches, eye strain. Long-term, kidney damage. You can have irritation through skin contact. And one particular chemical is a potential human carcinogen. And these are products that we use, and we use them every day, but in the wrong situation, exposure to them is not a good thing. And there are guidelines and that have to be followed. So bulk fuel storage, especially in the northern communities, because of the remote access, there's large quantities of fuel stored because you can only get fuel in there in large quantities once a year. So you have very large quantities of fuel storage. Gas stations that they're either a commercial station like this or just people having their own gas stations for their own personal use, or a small gas station. Heating oil tanks, these are especially problematic because they're located right next to the building they're heating. So if you have a release there, it ends up impacting either the residence, the dwelling, or maybe a commercial building, and it might mean that building is no longer occupiable or usable for the moment. And again, motor oils, all of these products are used. And again, these containers, even after the product is used, there's still residue left in that container. They often end up in the landfill. And when you have a number of containers over a number of years, the hydrocarbons can become a problem at the landfill as well. PCBs, they were an insulating oil used in transformers and fluorescent light ballasts. There are not many, again, in use at this time. Most of them have been pulled out of service, but there may be, maybe waste or historical spills that PCBs might show up as a problematic chemical. Again, transformers, especially out-of-use transformers, older fluorescent light ballast, the ballast in there that sort of powers the lights. They sometimes had PCBs as an insulating oil in them. Usually you can determine from the label, there's a list where you can check the labels on the ballast, and that we can tell you whether they're PCB containing or potentially PCB containing, and all the new ones are typically labeled non-PCB containing. Solvents, degreasers, or chemicals used in oil-based paints, nail polish remover, those are just some common. Varsol is something everyone might have heard of. And again, they have health effects if you're exposed to them through breathing, inhalation primarily, or ingestion. Those are just an example of paints and solvents on a shelf. And wood preservatives, which is not as common, but it can be an issue. Used to preserve wood from rotting. Railway ties, creosote, pentachlorophenol, and chromium copper arsenate, which are your typical fence post treaters. And again, they have specific health effects, potential health effects if you're exposed to them. Those products, though, are out of use now for consumer applications, but they still exist out there from previous construction. And they can leach a little bit. They're not very mobile, but they can. There was a concern in Toronto a little while back about potential for kids playing on playgrounds, equipment that had been treated with the preservatives. So you've got utility poles storage and playground equipment that may have been treated with these products. And glycol, that's antifreeze. The problem with glycols, they're very soluble in water. So once they get into the environment, they're very mobile and they can move quite quickly and contaminate a drinking water well or something like that that's nearby. And I think, dangerous if they're ingested in large quantities. And that's just a drum of glycol. So another, which isn't a particular product, it's more of a situation, are waste disposal sites. And everything ends up eventually into the garbage dump. And oftentimes the garbage dumps that are in the communities are sort of spontaneous, or they've been developed just because of the need to have to put garbage somewhere. They're not necessarily an engineered landfill, they're not necessarily sited in the best location, but the waste has to go somewhere. And so everything ends up in the landfill. It could be domestic, commercial, industrial, solid and liquid wastes, from metals, plastics, cleaners, dyes and ink in paper will leach out, tires, batteries, and the lead and acid in batteries. Electronics are becoming more of a problem because they use all kinds of heavy metals and metals in the circuit board in the electronics, and they get disposed of as well into a landfill and start to break down and leach out, and of course fuels, paints, and antifreeze. And that's what we call the soup that's made when all the waste is in the landfill, and the rain and the snow percolates through the waste, and you get all the different chemical reactions happening with the different products, and it's called leachate. And so that can contain hundreds of different chemicals. And also the problem is it's not just one chemical, but many chemicals reacting together, which you're not sure what that's going to form. And some of the chemicals can increase the mobility of other chemicals by lowering the pH in the ground. It makes metals more mobile, and they can start to move where in a normal situation they wouldn't move. So you have all different kinds of potential carcinogens, heavy metals, and also if the water gets into your drinking water well, it can definitely impact the taste and the odor of your well and make it non-drinkable not even necessarily from a health perspective, but just the water doesn't taste well or doesn't look good anymore. So there's solid waste, just a garbage dump. Everything pretty much ends up in it. There's not necessarily much in the way of segregation. Scrap vehicles. And waste liquids as well. That's in the northern communities, again, a big problem because the cost involved in properly removing and disposing liquid wastes. Very expensive to ship liquid waste out over the winter road and dispose of them properly at a licensed disposal. They have to go to a Ministry of Environment licensed disposal facility. They have to be hauled by a Ministry of Environment licensed waste hauler, and all of those things cost money. And you can only ship them out once a year on the winter road, essentially. So they are a large issue in the northern remote communities and in the southern communities as well. Another sort of category is wastewater. All the water that we use for bathing and washing and any maybe in industrial processes, that becomes waste as well. And it should be treated before it's discharged to the environment. And sometimes it is, sometimes it isn't, sometimes it isn't fully treated. An example of that is sewage lagoons. Eventually you have to discharge your lagoon. It doesn't hold infinite amount of water, and hopefully it's operating properly so it has the proper retention time to treat the sewage that goes into it. Septic fields, that's something more common maybe in the south, where each house or building would have a septic field, the same sort of situation where your wastes go to that field, and it needs to be constructed properly to treat the sewage properly before it gets out to receptors. Storm sewer and surface water runoff as well in communities that may have storm sewer systems, or just running off of down the road and into the lake, picking up whatever's it can pick up on the way. So the things we worry about with wastewater discharge, microorganisms, potentially germs basically, or bugs that could, if you drink, it could make you ill. Those would be the ones that are a problem or classified as pathogens, but typically you sample for sort of indicator organisms that would indicate the presence of a pathogen. Total or fecal coliforms and E. coli are some tests that are done to see if there's the potential for impact by microorganisms that could be a problem to human health if ingested. And nutrients. When people and animals excrete waste, it's high in nutrients, urea, and that can lead to what's called eutrophication. If it gets into a water body in large quantities, those nutrients allow the algae, the natural algae in that water body, to bloom and grow very rapidly, and that can create a depletion in oxygen because they're sucking all the oxygen out of the water, and it can cause death or hazard to aquatic life, especially those things that can't move. Fish may be able to escape an area of low oxygen, but the insects, the crayfish, the clams and mussels and those kinds of things which can't move can die from an algae bloom and lack of oxygen. So that's just your typical sewage lagoon. In facultative sewage lagoon, that's an example. I'm not sure if everybody knows how a septic field works, but your waste goes to a series of pipes. Well, it has a tank where you take out the solids, and then the liquid continues on to a series of pipes which drain into the ground, and the natural processes in the earth break that sewage waste down to non-harmful chemicals. But if it's not constructed properly, if you're overloading the capacity of the field, those wastes can get into the environment, into the water table, and you could drink them in your well potentially as well, and suffer some effects from that. Other issues which I'm not going to talk in detail about, but we know mining is a big issue in this area, and it has its potential environmental impacts. Pulp and paper, any other kind of industry, metal plating, anything, sawmills, everything has a potential environmental impact. Agricultural runoff, that's related to the same kind of problems with the wastewater. Traditional foods, that's something that's often in the news, or there are chemicals that are persistent in the environment, and like PCBs or mercury or those kind of things, which can travel long distances through the climate, through the atmosphere, and end up in places where you wouldn't expect them to be because there's no industry, and they can build up over time. They can bioaccumulate, which means, if it gets into somehow gets into an insect, eats something that's impacted, and then a larger fish eats that insect, and then a bigger fish eats 20 of those insects, and then that bigger fish eats 20 of the smaller fish, that those chemicals can build up in concentration, and by the time we eat them, there could be a health problem with that. Air, mold is another big issue that's arising. Oftentimes mold is a problem with building construction, or sometimes because in the communities we're trying to fit 20 people into a building that should house 5 people or 6 people, and we make a lot of moisture by breathing and showering and cooking, and it builds up inside of the house and create mold. And noise. Noise can be an environmental impairment as well. If you're living next to a noisy factory or a railway or something like that, noise can actually have a health impact or an environmental impact as well. Light, absolutely. If you're working in a building with poor lighting, and those are things that can be, there are standards for noise, standards for light, and they can be measured and adjusted to make a better environment for everyone. So sampling, so we've got these problems, and we want to test and see if we do have a problem in the area where we're looking at. So sampling can be part of what we call an environmental site assessment, which is looking at a particular site. Maybe we're looking at like a gas station, or it used to be a gas station. And you want to look and see if there's concentrations if there's contaminants at a particular location and a particular time in space. You can do baseline sampling, say if somebody was looking at opening up a mine. You want to see if you want to in the future determine if that mine is going to have any effect or having any effect, you need to know what the conditions are before that mine opened up, what the baseline conditions are. And again, after you've opened the mine up, or maybe you have a landfill, you want to do ongoing sampling and monitoring to make sure that conditions are not changing, or whatever you're doing to mitigate that problem is successful. Those are some reasons you might want to do sampling. So there's sort of two measurements. We have meters and probes and things that can measure things in the field. They can measure vapors, they can measure water levels, you can measure levels of oxygen in the water, all different kinds of things in the field. And then you can also collect samples of soil, water, air, and you can send those away to a lab and have the actual concentrations of whatever particular potential contaminant you're looking at. They can be quantified by the laboratory. And so you have a number, and you'll compare that concentration to a regulatory criteria, which gives you an idea if that concentration, there's a potential environmental or health effect with that parameter at that concentration. And you take that information and you interpret it, all the data, with other site conditions, and at the end you typically prepare a report defining the degree and extent of the impact, and it may include what you can do to address that impact or clean it up or mitigate it. So soil sampling. Sort of 3 methods here of soil sampling that I've shown. First one is just test pitting with an excavator or a backhoe. You dig down through the soil, through the area where you're trying to test. You log the soil conditions, what type of soil, what the moisture content is in the soil, any fill materials, any garbage, debris, anything like that. And then you can collect samples throughout that profile and field screen them for vapors. And then you can select a sample that you want to send into the laboratory for quantification of whatever you're looking for. You can use a big machine, an excavator as well, if you have to go really deep. And when you're done, you fill the hole in. You can't leave the holes lying around over. That's a health and safety issue. So, hand augering, sometimes they're a very useful tool, especially in remote communities. This is a hand auger that we typically use. It comes in sections that go together, and you can put other sections in, and you can see the guys are down. We get down 20 feet in the right soil conditions or more. You collect the sample from the head of the auger as it comes out, especially if the hole will stay open in the right soil conditions, and then you can put the sample in a polyethylene bag and then do some field screening on it. Just showing next to a day tank where you can get right close to the tank and do some testing. Inside buildings where you can't get an excavator or a drill rig, which we'll talk about a little bit later. And you can also do sediment sampling, which is a little bit different than soil sampling, but that's just showing sediment is into the lake environment, or the aquatic environment, the bottom of the lake, and you can collect samples from there if you're worried about or concerned about sediment as well. This is a drill rig, a truck-mounted drill rig. It's a typical instrument used for sampling or environmental site assessments. Auger, typically using rotary auger. This is a skidder-mounted rig for a little bit, maybe more off-road environments. And it drills a hole with, this is a small track-mounted rig that can actually break down, get on a plane, on a hawker, and be flown into a remote community. So it typically has an auger that screws down into the soil, the ease of which is dictated by the soil type, and makes a hole. That's a solid stem auger. You can also use a hollow stem auger, which then you can sample down the center of the auger, and it stops any caving of soil from the outside, so you get don't have to worry as much about soil from the sidewalls falling into the borehole. We call it a borehole, was what we're creating. You can sample from the auger flights if the soil conditions don't allow you to split spoon, but typically we in a hollow stem auger or in a hole where you've pulled a solid stem out, it's a two-sided metal tube that's hammered into the soil, and you bring it up and you split it open, and it gives you an undisturbed soil sample. So you have an idea of what the stratigraphy of the soil is, and you can collect samples that you can be fairly certain of what depth the sample was collected at. And so that's just a scene where the drill rig is working and collecting the samples, and we got the field technicians collecting the samples from the drill rig, conducting some field screening on them. The sample gets split. Part of it would go into a jar for potential laboratory analysis if we're looking at sending that sample to lab. And then the other half would be screened for organic vapors, and that's a photoionization detector, a PID, which we have one over here, and it'll give a measurement of the amount of vapors being created from that potential contaminant, if that contaminant is something that would release vapors, like a hydrocarbon, a fuel or something like that. It's not going to measure metals or anything like that. It has to release a vapor. And that's a combustible gas meter. It's a similar, it measures the vapors in the soil, but in a little bit different way. So then, so that's soil sampling. Now water sampling can be groundwater. Everywhere we are, everywhere in the environment, at some point below us is groundwater. It's basically where the pores in the soil are full of water. And that's where we get drinking water from if somebody has a domestic well. And eventually all groundwater exits into surface water as well. So there can be movement through groundwater and into surface water into your lakes, streams, and rivers. You can sample the surface water directly, and that could include, say, runoff ditches or as well as lakes and rivers. And you can sometimes want to sample the potable water supply, the drinking water supply, either if it's from a well or from a treatment plant. Sometimes the lake water is the potable water supply, and people are getting their water right from the lake. So this shows a little schematic of how, in this case, fuel impact would enter the environment from a spill at a tank, going down through the soil vertically under the force of gravity. It will go down as long as the pore spaces aren't full of water until it hits what we call the groundwater table, where at that point the pore spaces are full of water. And then it'll move, and all groundwater is flowing. Just like lakes are flowing and rivers are flowing, groundwater has movement and direction to it. And the fuel contamination will then start to move in the direction of groundwater flow, which typically is towards the nearest surface water body, but not always the case. So you get, and in fuel's case, some of it is soluble or will dissolve in the groundwater. So that would show the green plume there. That's dissolved fuel into the water. And then you might have what we call free product or liquid phase product, where it's actually floating. Fuel is actually floating on top of the groundwater table. And in this, I wonder if I can talk about the wells later. So we talked earlier about boreholes, and a way to allow collection of a groundwater sample is installation of what we call a monitoring well, which is a sort of a scaled down version of a drinking water well. So we installed typically a PVC pipe, and this would be an example of the pipe. The bottom end is the screen or slotted, which allows the water to enter. There would be a filter pack of sand placed around this to filter out fines. And then we would, there's the sand going down around the well, around the screen portion. And this is a well, a cross-section of a well. And the important part is that the hole that's been drilled has to be sealed from the surface. Otherwise, surface water will just run down your well. It won't give you an accurate representation of the groundwater, and you could potentially contaminate the groundwater as well if something bad got down your hole. So it's critical that the well is sealed up to surface, and for that we use it's called a bentonite clay. It's a clay that when it gets wet or when it hydrates, it swells up many times its size and will block off that hole. So it won't allow water to get down what we call the annulus of the well, or just the area of the borehole around the well pipe. So that's just another showing a finished well with lockable protection. They all have to be locked so they're secure and nobody can tamper with them and pour anything down them. That's another well close to the lake. Sometimes you do it and maybe you're in a parking lot at a gas station. You can't have these stick-ups all over the place. They won't last very long. So we put a flush mount well protection in there, and that's the top of the well pipe. The top comes off and you can sample the well down there. So there's a couple ways of sampling. In a lot of the remote communities, we use what's called it's a Waterra, which is a brand name, or it's a polyethylene tubing with a little foot valve on it. It's just basically plastic tubing, and it has a little foot valve, and as you move it down and move it up, the water inches up the tube and comes out the end. It's a very simple system. There it is there, and that's all it is. Basically it's a pump, a person-powered pump, but a pump. And that we can also use a baler, which is a similar situation where you lower this down the well on a string, the water pushes up the little ball, and when you start to pull it, the water covers the hole, and you can collect a sample of the water in this. In this case, that's actually fuel, not water. That was floating on top of the water in the hole. Bit of a contaminated site. Peristaltic pump. We have a peristaltic pump over there. It's a pump which spins little wheels around a tube and draws the water up. And it's good for what we call low flow sampling, which is a little bit, I won't get into that, but it's just another pump that can run on a battery, and you can take it out in the field, put the end of the tube down into the water, and you can draw a sample up into whatever sample container that you need to fill for whatever you're looking for. Can also do, again, the field screening. We can pump water up and then screen it for things that pH, conductivity, dissolved oxygen, temperature. It depends on what, say in a landfill situation, these might be parameters that you want to measure and give some indication if the leachate is migrating underground. And we have an oil-water interface probe, which is over there, and that actually can measure the depth to the groundwater, but it also can measure if there's fuel or free product on top. Do you want to do that, Simon? Sure. So in this case, it's cooking oil, which is the product that's floating on top. And when you send that down a well, if there is fuel floating on top of the water, when it gets to the fuel, it'll make a solid tone. Come on, Simon. It's coated with that cooking oil right now. There we go. So when it makes a different tone in water. So the water started and get the thickness of the product that happens to be floating down there. It works on, there's two little probes, conductivity probes that fuel is non-conductive. So if those two little probes, and it also has an optical density meter, so it knows when it goes from liquid air into liquid, it says, okay, I've gone into liquid. And if the probes can't talk to each other, it knows that that's a non-conductive liquid.
When you did that, was there some residual contamination on the top?
Well, this
give you a false reading.
Well, that's cooking oil is very sticky. It's not like diesel fuel. If we had a spill of cooking oil, I guess it would be a tough one to measure. But gas and diesel works a little better. We just didn't want to have gas or diesel in our
They just
little
coated the
beaker.
probe a little, that's all.
Yeah. Good question, though.
Well, and
So
this
there's-
has values as well, right?
That's one of the things that we teach our field technicians is to.
Don't just believe the
Don't
measurement.
do your first measurement.
Yeah.
Do it 3, 4, 5
5 times.
times, whatever, until it's
Till
consistent.
it's-
Probably use descriptors for more cooking oil, right?
Yes. There's the oil water interface probe. So it's measured, and sometimes there is no fuel, and we'll just measure the groundwater table elevations or the depth to groundwater. Again, that's important too, depth to groundwater, because we can survey the wells in and do depths to groundwater, and we can get what's called a gradient. We can tell which way the groundwater is flowing by this well might be higher than that well, and you can see which way the groundwater is flowing with the gradient. That's again a baler. You can measure LPH, or that's liquid petroleum hydrocarbons, or free product with the baler as well, thickness of product in a well. So we can also, as we saw on that last slide, that usually groundwater is exiting to surface water, or you might have a spill over land and you're concerned about impact on surface water body. And you can take samples from the near shoreline. You can also take samples from out in the lake in a boat. So this tool here is something that you can take out into the lake and lower down on a rope from a boat. And when you get the sampler at the desired depth, you can send down it's called a messenger. A messenger.
You can also lose fingers pretty quick.
Yeah. Send down a messenger which releases the. Yeah. Yeah.
So it goes down when it's open like that?
Yeah.
Okay.
Yeah. Yeah, and then you leave it for a certain amount of time. Well, you'll leave it for a certain amount of time, and it will equilibrate and get the local water. Yeah. Did it open? Anyway, they're actually going to do it. So you lower that down into the lake to whatever depth you want. If it's a deep lake, you might go 100 feet down, or 50 feet down, or 10 feet down. You send down the messenger at the desired depth, and it'll release the.
Yep, so you drop this from the boat.
Yeah.
Let her go.
Yep, I'll just let it go.
So you drop that down underwater, and then you drop this from the boat, and
it'll collect the sample where you
catches
want
your
it.
water, and you bring it up.
Yeah.
Then it's got a little valve, and you just pour it into your bottles. For sure.
Yeah.
And all my fingers and toes left.
Yeah. I like this.
This is just showing another collection of a sample, a surface water sample. This is actually from some drainage from a mine or an old tailings. Yeah, acid mine drainage. Just a little colorful slide I thought I'd add. Sulfur, that's because of the high sulfur content in the water, the yellow color.
Would you be sampling like that though, no protection on the face or anything?
Yeah, just with she'll have gloves on and she's got the rain suit. I'm guessing that's because it's a rainy day, but yeah, there's not much in the way of vapors coming out of that.
Backsplash to get it in.
Well, you might want to wear glasses. That probably is a low pH situation.
I can see for sure it was.
Yeah.
I was there that
Okay. And here again, the field measurements, pH, conductivity, dissolved oxygen, temperature, those kind of things with the probes in the field. Some of these things are hard to send samples in for the lab, because things like dissolved oxygen, that has to get to the lab extremely fast to measure. Well, even that. And also flow. You might want to measure flow, how fast the stream is flowing. And there's just a little sort of a propeller that spins through the current. The current spins the propeller and turns a meter. And the last thing we talked about is sometimes you may have a domestic well, your water supply might be right there at your house or in the area of a spill, or your water intake for your treatment plant might be nearby where there's been a problem, and you might want to test your drinking water. So you can test it from the tap, but you have to make sure that there's no treatment upstream of that. There's no filters or treatment that's cleaning the water before you get it from the tap.
So that's like a raw water sample.
Yeah, a raw water sample is, yeah, exactly. In this case, from a well. Or you can go right to the water treatment plant and collect a sample. There's usually somewhere where the guys there that are running the plant have a point where they collect their samples from, and we would do the same thing. So lastly, you've collected these samples, soil, water, whatever, and you want to know what's in them and how much, and we send them to a lab. They're an accredited lab, which means they're basically they're licensed, or they have the proper qualifications, and not only that, but that they can analyze the particular contaminant you're looking for, because not all labs can and not all facilities can. And typically they'll present a result in parts per million or parts per billion of a contaminant, maybe in percent or something. But so you receive that, and then you can compare those numbers against the typical regulatory criteria, government, federal, provincial, the standards, the guidelines, or whatever's out there for your contaminant.